In physical chemistry, the van der Waals force, named after Dutch scientist Johannes Diderik van der Waals, is the sum of the attractive or repulsive forces between molecules other than those due to covalent bonds or the electrostatic interaction of ions with one another or with neutral molecules or charged molecules. The term includes force between two permanent dipoles, force between a permanent dipole and a corresponding induced dipole, force between two instantaneously induced dipoles. It is also sometimes used loosely as a synonym for the totality of intermolecular forces. Van der Waals forces are relatively weak compared to covalent bonds, but play a fundamental role in fields as diverse as supramolecular chemistry, structural biology, polymer science, nanotechnology, surface science, and condensed matter physics. Van der Waals forces define many properties of organic compounds, including their solubility in polar and nonpolar media. In low molecular weight alcohols, the hydrogen bonding properties of the polar hydroxyl group dominate the weaker van der Waals interactions. In higher molecular weight alcohols, the properties of the nonpolar hydrocarbon chain, S, dominate and define the solubility. Van der Waals forces quickly vanish at longer distances between interacting molecules. In 2012, the first direct measurements of the strength of the van der Waals force for a single organic molecule bound to a metal surface was made via atomic force microscopy and corroborated with density functional calculations. Definition: Van der Waals forces include attractions and repulsions between atoms, molecules, and surfaces, as well as other intermolecular forces. They differ from covalent and ionic bonding in that they are caused by correlations in the fluctuating polarizations of nearby particles. Intermolecular forces have four major contributions: a repulsive component resulting from the Pauli exclusion principle that prevents the collapse of molecules. Attractive or repulsive electrostatic interactions between permanent charges, dipoles, quadrupoles, and in general between permanent multipoles. The electrostatic interaction is sometimes called the Keesom interaction or Keesom force after Willem Hendrik Keesom. Induction, which is the attractive interaction between a permanent multipole on one molecule with an induced multipole on another. This interaction is sometimes called Debye force after Peter J. W. Debye. Dispersion, which is the attractive interaction between any pair of molecules, including nonpolar atoms, arising from the interactions of instantaneous multipoles. Returning to nomenclature, different texts refer to different things using the term van der Waals force. Some texts describe the van der Waals force as the totality of forces. Others mean all the attractive forces. All intermolecular van der Waals forces are anisotropic, which means that they depend on the relative orientation of the molecules. The induction and dispersion interactions are always attractive, irrespective of orientation, but the electrostatic interaction changes sign upon rotation of the molecules. That is, the electrostatic force can be attractive or repulsive, depending on the mutual orientation of the molecules. When molecules are in thermal motion, as they are in the gas and liquid phase, the electrostatic force is averaged out to a large extent, because the molecules thermally rotate and thus probe both repulsive and attractive parts of the electrostatic force. Sometimes this effect is expressed by the statement that random thermal motion around room temperature can usually overcome or disrupt them. Clearly, the thermal averaging effect is much less pronounced for the attractive induction and dispersion forces. The Lennard-Jones potential is often used as an approximate model for the isotropic part of a total van der Waals force as a function of distance. Van der Waals forces are responsible for certain cases of pressure broadening of spectral lines and the formation of van der Waals molecules. The London van der Waals forces are related to the Casimir effect for dielectric media, the former being the microscopic description of the latter bulk property. The first detailed calculations of this were done in 1955 by E. M. Lifshitz. A general theory of Lifshitz van der Waals forces was developed in 1961 by I. E. Zyaloshinsky, al. In 2011, Y. Zhang and Einar Nasami provided an alternate formalism for calculating van der Waals or Casimir pressure. London dispersion force. London dispersion forces, named after the German-American physicist Fritz London, are weak intermolecular forces that arise from the interactive forces between instantaneous multipoles in molecules without permanent multipole moments. These forces dominate the interaction of nonpolar molecules, and also play a less significant role in van der Waals forces than molecules containing permanent dipoles or ionized molecules. London dispersion forces are also known as dispersion forces, London forces, or instantaneous dipolar Euro-induced dipole forces. They increase with the molar mass, causing a higher boiling point especially for the halogen group. Van der Waals forces between macroscopic objects. For macroscopic bodies with known volumes and numbers of atoms or molecules per unit volume, the total van der Waals force is often computed based on the microscopic theory as the sum over all interacting pairs. It is necessary to integrate over the total volume of the object, which makes the calculation dependent on the object's shapes. For example, the van der Waals interaction energy between spherical bodies of radii O1 and O2 and with smooth surfaces was approximated in 1937 by Homaker by, where A is the Homaker coefficient, which is a constant that depends on the material properties, and Z is the center-to-center distance. That is, the sum of R1, R2, and R. In the limit of close approach, the spheres are sufficiently large compared to the distance between them. That is, so that equation for the potential energy function simplifies to the van der Waals force between two spheres of constant radii is then a function of separation since the force on an object is the negative or the derivative of the potential energy function. This yields the van der Waals forces between objects with other geometries using the Homaker model have been published in the literature. From the expression above, it is seen that the van der Waals force decreases with decreasing particle size. Nevertheless, the strength of inertial forces, such as gravity and drag lift, decrease to a greater extent. Consequently, the van der Waals forces become dominant for collections of very small particles such as very fine-grained dry powders even though the force of attraction is smaller in magnitude than it is for larger particles of the same substance. Such powders are said to be cohesive, meaning they are not as easily fluidized or pneumatically conveyed as easily as their more coarse-grained counterparts. Generally, free flow occurs with particles greater than about 250 I1/4 m. The van der Waals force of adhesion is also dependent on the surface topography. If there are surface asperities, or protuberances, that result in a greater total area of contact between two particles or between a particle and a wall, this increases the van der Waals force of attraction as well as the tendency for mechanical interlocking. The microscopic theory assumes pairwise additivity. It neglects many body interactions and retardation. A more rigorous approach accounting for these effects, called the macroscopic theory, was developed by Lifshitz in 1956. Langbein derived a much more cumbersome exact expression in 1970 for spherical bodies within the framework of the Lifshitz theory while a simpler macroscopic model approximation had been made by D. Jaguin as early as 1934. Expressions for the van der Waals forces for many different geometries using the Lifshitz theory have likewise been published. Use by geckos. The ability of geckos which can hang on a glass surface using only one toe to climb on shear surfaces has been attributed to the van der Waals forces between these surfaces and the spatulae, or microscopic projections, which cover the hair-like setae found on their footpads. A later study suggested that capillary adhesion might play a role, but that hypothesis has been rejected by more recent studies. There were efforts in 2008 to create a dry glue that exploits the effect, and success was achieved in 2011 to create an adhesive tape on similar grounds. In 2011, a paper was published relating the effect to both Velcro-like hairs and the presence of lipids in gecko footprints. In modern technology, in May 2014, DARPA demonstrated the latest iteration of its GEC-skin by having a 100 kg researcher's scale and 8 m tall glass wall using only 2 climbing paddles. Tests are ongoing, but DARPA hopes one day to make the technology available for military use, giving soldiers Spider-Man-like abilities in urban combat. See also, stochastic electrodynamics, references. Further reading, Ivor Breivik, V. N. Murakowski, Kimball A. Milton, Identity of the Van der Waals Force and the Casimir Effect and the Irrelevance of These Phenomena to Sonoluminescence, Hep Th/9901011, I. D. Zyalishinskaya, E. M. Lifshitz, and L. P. Petrivska, USP. Phys. Nork 73, 381, English translation, Soviet Phys. USP 4, 153. L. D. Landor and E. M. Lifshitz, Electrodynamics of Continuous Media, Pergamon, Oxford, 1960, ppA 368-376. Dieter Langbeen, Dietary Theory of Van der Waals Attraction, Mark Lefers, Van der Waals Dispersion Force. Holmgren Lab. E. M. Lifshitz, Z. H. EKSP. TO. Phys 29, 894, English translation, Soviet Phys. JETP 2, 73. Western Oregon University's London Force. Intermolecular Forces, J. Leichlemer, Fundamentals of Interface and Colloid Science, page 4.43, Israelishvili J., Intermolecular and Surface Forces, Academic Press, ISBN 0-12-375181-0. External links, Sinise, Fred. What are Van der Waals Forces? Frostburg State University. Retrieved March 2010. An introductory description of the Van der Waals Force, Robert Full, Learning from the Gecko's Tail. TED talk on biomimicry, including applications of Van der Waals Force.